On a clear night sky, a lot of stars become visible and shine in different magnitude and color. Some appear to twinkle, while others appear to be strong. Some celestial bodies appear excessively large and luminous, such as the sun and other moon. But these characteristics highly depend on their distances to the observer and how fast do they move in space. In this video, we will explain how the speeds and distances of far-off objects are estimated. The branch of astronomy that deals with the motions of celestial bodies is called celestial mechanics. Astronomers studying celestial mechanics usually estimate the speed and distances of celestial objects. Take note, however, that there is no single method that can be used to measure the distances of all celestial bodies that can be seen from Earth. The most common among the methods of measuring distances is the cosmic distance ladder. This method is composed of several methods that are built on one another. The data obtained in the first step of the ladder are used in the succeeding step, and so on. Let us have the anatomy of this ladder. The base of this cosmic distance ladder is a distance measurement done directly without any assumptions about the star's characteristics. For example, the measurement of one astronomical unit, or AU, which is the measure of the distance of Earth from the Sun, is considered the base. Thus, 1 AU is approximately about 1.50 times 10 raised to 11 meters. This same value is used in measuring the parallax of stars. When we say parallax, it is the apparent change in the position of an object due to change in the way we perceived it. Depending on the perceptions of the viewer, it is used in measuring the distance of the stars that are approximately 300 light years away. How is this star parallax measured? Usually, astronomers take a picture of a specific star, wait for 6 months to pass so that the Earth has moved for about 2 astronomical units, and then take a photo of the same star to compare the change in its position. Let us take this for example. Here, astronomers take a photo of Pleiades, an open star cluster which is among the nearest star cluster on Earth and the most obvious to the naked eye in the night sky. This is taken in August. After 6 months in February, they take another photo. The image of a star appears to shift slightly because of the change in position of how the star was seen. These shifts then serve as the angles of the isosceles triangle formed in the perception of the viewers from Earth. Here, in our figure, it forms a parallax angle measured in arc seconds. We remember that 1 degree is equal to 1 over 360 degree of a circle, and 1 arc second is equal to 1 over 3600 of a degree. We can establish the relationship between a star's distance and its parallax angle as d is equal to 1 over p. Usually, this distance is expressed in units of parsec, but a more common unit used to denote distances of celestial objects is light year. A light year is defined as the distance light can travel in 1 year. Here, I will present you the conversion factor among light year, parsec, and meters. 1 light year is equal to 0.306601 parsec, is equal to 9.461 times 10 raised to 15 meters. Let us concretize this by applying this in a formula. Alpha Centauri has a parallax angle of 0.742 arcsec. What is the distance between Earth and Alpha Centauri using the parallax method? First, We identified that what is asked in the problem is a distance between the Earth and Alpha Centauri. The given is the parallax angle of the Alpha Centauri, which is equal to 0.742 rsec. We can compute this problem using formula d is equal to 1 over p. Let us substitute the value of parallax angle, as d is equal to 1 over 0.742 rsec. Therefore, the distance is computed as 1.35 parsec. Now, you may want to express this in light year, the most common unit in measuring astronomical distance, or in meters, so we can have a better idea. First, we will multiply our computed distance, 1.35 parsec, to our conversion factor, 1 light year over 0.306601 parsec. We cancel the units parsec, leaving us light year. As we perform this operation, we will get 4.403 light years. We may want to further convert this to meters by multiplying to our conversion factor 9.461 times 10 raised to 11 meters over 1 light year. We cancel the unit light year, and finally, our answer is 4.16 times 10 raised to 16 meters. Therefore, the distance between the Earth and Alpha Centauri is 1.35 parsec, or 4.403 light years, or 4.16 times 10 raised to 16 meters. Let us have another example. Rigel Centaurus is the third brightest star in the night sky. Determine its parallax angle if it's 1.318 parsec away from Earth. After we identify the required quantity, which is parallax angle, and distance of 1.318 parsec, we can compute this using a derived formula, P is equal to 1 over D. We will substitute the value of D in our equation. Then, we will perform the operation as indicated. 1 divided by 1.318 parsec, and the final answer is 0.759 rsec. This is the parallax angle of the Rigel Centaurus. The parallax method can only be used to measure the distance to stars close enough to observe a measurable parallax, or about 100 parsecs, or approximately 326 light years from Earth. For stars whose parallax cannot be measured using the latter, the spectroscopic method is used. A spectroscopic method requires that the star's apparent brightness and spectrum be observed first. To do this method, we have to consider for absolute brightness of a star. The absolute brightness is the standard measure of brightness in astronomy. It is the brightness of a star that is 10 parsec away from Earth. The actual brightness of the star can be seen on Earth is known as its apparent brightness. Astronomers are able to determine the spectral type of a star's spectrum by analyzing its spectral lines and plotting the observations in the Hertzsprung-Russell diagram. This diagram shows a star's luminosity versus its temperature. This becomes an important tool for determining the distance of far-off objects, because the astronomers believe that the stars near Earth are similar to the stars far from the Earth. If the star's location can be plotted on the HR diagram, its absolute brightness can be read off. Knowing this absolute brightness of a cluster of stars and comparing this brightness to the absolute brightness of the stars with known distance enabled the astronomers to roughly estimate the distance of that cluster from Earth. This observed cluster is shifted vertically in the HR diagram until it overlaps with the model star, or that star with known distance. Then, their magnitude is compared, where the difference is called distance modulus. This distance modulus, or the difference between apparent and absolute magnitude, which we represent as small m minus big M, is the direct measure of the distance of the star. By formula, we can express this as m minus m is equal to 5 log d minus 5, where m, or the small m, is the apparent magnitude, the big letter M is the absolute magnitude, and d is the distance to the object in parsec. In the next video, we will have some concrete problems to determine some distances of stars that can be achieved using a spectroscopy method and finding the distance modulus. That's all for today. This is Gilmar De Castro, and see you in the next video.